Find the nominal moment in the beam in pounds-feet. In this problem, a simply supported beam is subjected to a constant moment, Mn. A cross-section of the beam shows the beam width is 10 inches and 5 size 10 reinforcing bars are positioned with an effective depth of 18 inches from the top of the beam. The yield stress and modulus of elasticity of the steel are provided, as well as the compressive stress and maximum strain in the concrete. From moment equilibrium, the nominal moment equals the tensile force developed in the steel times the effective depth minus A divided by 2, where A equals beta times C. In this equation, C is the distance from the top of the beam to the neutral axis, which is the axis where the strain equals 0. And beta is a function of the compressive strength of the concrete and ranges from 0.65 to 0.85. Since the compressive strength in the concrete is 4,000 pounds per inch squared, the value of beta equals 0.85. For now, we'll leave the variable A in the moment equilibrium equation and utilize the values of beta and C later. The tensile force in the steel equals the area of the steel, AS, times the tensile stress in the steel, FS. The cross-section shows the beam is constructed with 5 number 10 reinforcing bars of steel. The area of steel in one number 10 reinforcing bar can be looked up in a table and equals 1.27 inches squared. Therefore, the total area of steel equals 5 times 1.27 inches squared, or 6.35 inches squared. So far in the problem, we do not know the tensile stress in the steel at failure. We'll assume that when the concrete is failing in compression, the steel is yielding in tension, and the stress equals the yield stress of 40,000 pounds per square inch. Therefore, the assumed tensile force in the steel equals 254,000 pounds. To solve for the assumed value of A, we'll use the equation for axial force equilibrium, which states the tensile force developed in the steel equals the compressive force developed in the concrete. We already know the tensile force in the steel equals 254,000 pounds. So the compressive force in the concrete equals 0.85 times the compressive strength in the concrete times the area of concrete in compression. The compressive stress in the concrete is provided in the problem statement as 4,000 pounds per square inch. The area of concrete in compression equals B times A, where B is the 10-inch base width of the beam and A is calculated to be 7.47 inches. Before we can use 7.47 inches in the equation for the nominal moment, we have to confirm this assumption we made is valid, namely that the steel is yielding. We can determine if the steel is yielding by comparing the strain in the steel with the yield strain in the steel. If the strain in the steel is at least the yield strain in the steel, then the stress in the steel equals the yield stress, as we assumed, and A equals 7.47 inches. If the strain in the steel is less than the yield strain for the steel, then we'll have to recalculate the stress in the steel and recalculate the value of A. The strain in the steel, epsilon s, can be determined using strain compatibility. The problem states the maximum strain in the concrete, epsilon c max, equals 0.003. Therefore, using similar triangles and the values of C and D, we can compute the strain in the steel. From earlier, we calculated C equals A divided by beta. By plugging in our assumed 7.47 inches for A and 0.85 for beta, C calculates to 8.79 inches. After the values of C, D, and epsilon c max are plugged into the equation for the strain in the steel, the strain in the steel equals 0.00314. The yield strain in the steel, epsilon y, can be calculated as the yield stress in the steel, Fy, divided by the modulus of elasticity in the steel, E sub s. After plugging in the appropriate values, the yield strain in the steel equals 0.00138. Since the strain in the steel is indeed at least the yield strain in the steel, then our assumption was correct, and the value of A equals 7.47 inches. Returning to our equation for the nominal moment in the beam, the terms are plugged in for the tension force in the steel and for the lengths D and A. And the nominal moment in the beam equals 3.623 times 10 to the 6 pounds-inches. After converting the units to pounds-feet, the nominal moment in the beam equals 3.02 times 10 to the 5th pounds-feet. When reviewing the possible solutions, the answer is C.